Welcome to Unit 6 on Inference for Categorical Data, Proportions. In this video, we're going to cover topic 6.4, setting up a test for a population proportion. So the first thing you might be wondering is, what the heck is a test for a population proportion? Well, trust me, you're going to learn all about it in this video. But I want you to understand that this topic of a test for a population proportion actually spans 4 topics. Really 3 of the big topics. So we got 6.4, 6.5, 6.6, and it even gets into 6.7 as well. But again, it's going to be a long road for you to completely understand what a test for a population proportion is. This video is just the beginning of it. But I will say this, a test consists of 4 steps. In this topic, we are going to explore the first 2 steps. I'm also going to try to explain to you the overall idea, but we're only going to really kind of focus at the end of this video on those first 2 big steps. All right, so what is a test for a population proportion? Well, what we've already done in the previous 2 topics is cover confidence intervals. A confidence interval is we don't know the population proportion. We have no idea, so we use a sample to try to estimate it. Pretty straightforward. But now a test is different because in a test, a statement is made about the population proportion. However, someone believes the population proportion to either be higher or lower, or simply different than what we were told it was. So our job is to use a sample as evidence to help to see if the belief is true or not. Now, that's maybe not the best explanation, and certainly this is just the beginning of this, but here's an example that might make it a little bit more clear. A recent study found in a medical journal that 35% of adults have experienced depression sometime in their lives. Again, so that's something that we read. We read that the true proportion of adults who've experienced depression is 35%. But here's the kicker. David, the mayor of a large town in Vermont, believes that residents in his town are much happier and less have felt depressed. So he plans to collect a random sample of 350 people to hopefully prove that his town is less depressed than this national value. So this is where a test is needed, because we are given a true population proportion. We were told, we read, 35% of adults have experienced depression sometime in their lives. But David, this mayor, believes that his town is lower than that. So the only way we could prove that he is right is to put his belief to the test. So the first part of this is understand there's got to be a question of interest, right? So David's question of interest is, what proportion of people in my town are depressed, right? The national value is 35%, but David's question of interest is that he thinks his town is lower. So here's a couple more examples, right? Just to make sure you really understand what's happening here. So another example is I read that 40% of teenagers have braces. Okay, that's what I read the truth was, but wait a minute. I think it might be more. So that's my belief. My belief is that it's more than 40%. So the only way I could prove that belief is get a sample and put it to the test. I saw a report that 45% of house break-ins are by someone who knows the victim. So 45% of all houses that get broken into are done so by somebody who knows the victim. This seems kind of high to me. Is it lower? Okay, so my belief is that it's lower than 45%. So 45% is the true value. That's at least what I read. But I think it might be lower. Again, the only way I could test that is to get a sample and try to prove it. Here's a third example. A news report claimed that 62% of all teenagers experience daily anxiety. Boy, I wonder if that truth is something different than that. So I read that it's 62%. That's what somebody said the truth was. But I'm wondering if maybe at my school district it's something different. Higher, lower, don't really care, just something different. So every one of these examples, the question of interest is focusing on a proportion, right? Each question, that proportion is something different. But the idea is that a confidence interval is we don't know what the truth is, so we're going to try to find it. Here, we do know what the truth is. We're just wondering if it's something else. So to answer these questions, we essentially have to become detectives, right? We have to start with the assumed true population proportion and a thought about what the real truth is, right? Now, remember, when you're a detective, you're supposed to assume that the person is innocent. So that's what I'm going to do here. So I'm going to assume that what I read, I'm going to assume that the given population proportion is true, And I'm going to take my thought, I'm going to take my belief, and I'm going to try to see if there's evidence to support that. So in the examples that we just looked at, in the first example, the assumed truth is, well, that 40% of teenagers have braces. My belief, my thought is that it's higher. In the last example, the assumed truth was that 60% of teenagers experience daily anxiety. Okay, I'm going to assume that to be true. And then my belief or my thought is that it's something different. It's not 60%, it's something different. So our job is to act like a detective and gather evidence, right? Then we have to examine that evidence and see where it leads us. Does it lead us to say, well, maybe 40% is true? Or does it lead us to say, no way, it's definitely higher than 40%? And that's what we're going to be able to do. But again, it's going to take several topics for us to cover all this material. This is not the easiest thing, but I will say that every step is in itself pretty easy. It's just a matter of putting it all together. All right, so, how do we statistically answer these questions? Well, this is me kind of give you an overall idea. All the pieces and parts will be explored in the next couple videos, the next couple topics. But here's kind of the overall idea. It all starts with building a sampling distribution on the assumption that the population proportion given to us is true. Again, if the criminal who we arrested says he's innocent, we have to assume that that's true. And then we look for evidence to try to prove he's wrong. Or you know what? Sometimes the evidence proves he was right. So this sampling distribution allows us to see what all possible sample proportions will look like. Then what we could do is we could select a random sample from the population of interest and examine the sample proportion. Finally, we could see where that sample falls. So what we're going to actually do is we're going to build a sampling distribution centered at the true value that we were given. We could calculate the standard deviation. We could prove that the shape is normal, right? Then what we're going to do is we're going to find our sample. If our sample happens to fall in the middle somewhere, well, then that means it was likely to occur. It wasn't a weird value. And what that would tell us is that maybe what we read was true is still true, because it's not weird if you're only a little bit higher or lower. Or the other thing that could happen is maybe our sample comes back very, very significant. Really, really high on one of the tails, right? Either on the upper tail or the lower tail. Now, this does give us evidence that our thought's true. Because if we find a sample that should not happen if this is the truth in the middle, well, then that only gives us evidence that, listen, what we read was true is not true. It's the same idea. It's just not statistical. But, if in the middle's innocence, and we find this crazy evidence, this very significant evidence that shows the criminal did it, well, then we're going to go ahead and put him in jail. But if we only find mediocre evidence that it doesn't mean anything, right? Then we might have to let him free. All right. So this whole process does have a formal name. And you do need to know that name. It's going to be one of the steps that we'll talk about in a moment. But the name is a one-sample z-test for a population proportion. All right. Remember that name because you'll need to know it. Step one is just getting organized. Step one is all about getting organized. Remember, this is a 4-step process, and we're only going to cover the first 2 steps right now. But step one, it's really about just getting organized. Now, step one has 3 parts. They're all very easy. The first part is identifying the parameter of interest. All you're doing here is you're naming the population proportion that we're concerned with. I'm concerned with the proportion of kids that wear braces. I'm concerned with the proportion of teenagers that experience daily anxiety. You're just naming exactly what it is that you're interested in for the problem. And you don't have to make this up. It's going to be given to you in the problem. All right, then you have to name the test. This is important, right? You have to say, to answer the question, I need to use a one-sample z-test for a population proportion. And the third thing you need in step one is to build what we call the null and the alternative hypotheses. Now that we'd have to do a little bit more talking about. I don't expect you to know what that is, but we're going to explain it right now. But it's a lot like hypotheses in science class, right? When you're trying to do an experiment in science class, you start off with the hypotheses, something that you believe to be true, and then maybe an alternative hypothesis for what, could happen. And again, it's a little different than science class, obviously, but we'll explain it right now. So the hypotheses. All right. Every one-sample z-test has a pair of hypotheses. All right. There's a null hypothesis and an alternative hypothesis. The null hypothesis is the situation that is assumed correct unless evidence suggests otherwise. So the null hypothesis is what we read was true. It's the assumed true value for the population proportion. Now the symbol we use to denote the null hypothesis is a capital H for hypothesis and a little 0 here for the null hypothesis. Then we have the alternative hypothesis. This is the situation for which evidence is being collected. So this is our belief. This is our thought. This is our wonder. And this symbol is another H for hypothesis, but we use a little A there for the alternative hypothesis. Now, I get it. These two things might be a little foggy. What I'm going to try to do is give you some examples to really clear this up. So let's talk a little bit more about the null hypothesis. It always is using the population proportion, and it's always going to use an equal sign. Because again, this is what we read to be true. So for example, in the first problem I started you with is we read that 35% of adults experience depression. So our null would be that the true proportion of adults that experience depression is 35%. So we're going to use P, the true proportion. That's what we're testing. And we're going to use an equal sign because we have to assume that that value is true. That's the null. Now the alternative also uses the population proportion P, but it explores what we believe to be true. Now in the example that we started off with was we believe that the proportion of adults that experience depression in our town, or at least this mayor's town, is less than 35%. So again, notice I'm still using the true proportion P, but I'm investigating, I'm looking for evidence to show that it's less than 35%, 0.35. Now, other problems might use a greater than sign. For example, the problem with the braces, I thought that the truth was greater than 40%. Other problems might even use a not equal to sign. And the problem about teenagers with anxiety, I just cared that it was something different than the 60% I read. So that's the process, right? It's the alternative is using something other than an equal sign based on what we believe to be true. Let's actually go and practice this with these two specific examples. I read 40% of teenagers have braces. There's my null. My null hypothesis is that the truth is 40%. The alternative is what I wonder if it's higher, bigger than 40%. Simple. That's it. That's how easy the null and the alternative hypotheses are. In this next example, I read that 60% of teenagers experience daily anxiety, so that means the true proportion is 60%. I have to assume it's true. The alternative is what I'm wondering if it's something different. Now remember, different simply means not equal to 60%. Higher, lower, who cares? Now, we do actually have two more things that I want you to understand. Pretty easy, this isn't too complicated. But we have what's called a one-sided test and a two-sided test. A one-sided test is when the alternative only looks greater than or less than. So you're only looking at one side. You're either looking for evidence on the high side or evidence on the low side. A two-sided test is just a more specific name for looking at an alternative that is simply something other than the true proportion, right? It's just something different. So if we go back here, this first example would be a one-sided test because it only explores being greater than 40%. This example down here would be a two-sided test because I don't care if the number's higher or lower. I just care that it's something different. So this really isn't a big deal. You don't necessarily have to state that it's a one-sided test or two-sided test unless asked. So I did briefly want to go over so that way you understand what those two terms are. All right. So let's step back to this general idea, right? There are 4 steps. We're not going to learn them all in this video, but I do want you to get a basic idea of what a one sample Z test for a population proportion is all about. First step is all about those hypotheses. What do we believe to be true? And then what do we think? What do we know? What is our thought? What's the alternative that we want to be true? Then we have to check our conditions to build a sampling distribution. Because remember, in order for our sample to be truly understood, we need to compare it to all samples. So we have to build a sampling distribution assuming that the null hypothesis is true. We'll talk a lot more about that in a moment because we are going to cover step 2 in this video. The third step is what we're going to cover in the next topic. But here we're actually going to collect a random sample from the population of interest and get a sample proportion. When we do this, we're going to test, how likely is that sample proportion? Is it likely, meaning in the middle, or is it very unlikely, meaning it's very significant? It's way out on that upper or lower tail, meaning it shouldn't happen if the null is true. We'll explain all of that in far more detail in the next topic. Finally, we need to make a conclusion. What are we going to conclude? Are we going to conclude that the null hypothesis is possibly correct, or are we going to conclude that our alternative is true? And we're going to talk about that in topic 6.6. So lots more to come on this. Right now, we're just trying to get the general idea of what this test is all about. All right, so step 2. Once the test has been named and the hypotheses are established, it's time to move on to step 2. Step 2 is really easy because we already know how to do it. We spent an entire unit on sampling distributions. This should not be difficult. So here we're going to create a sampling distribution on the assumption that the null hypothesis is correct. Again, just like assuming that a arrested person is innocent before we, officially sentence them to jail or something like that. All right, so we have to find the mean, we got to find the standard deviation, and we got to find the shape of the sampling distribution, all on the assumption that the population proportion P is true from the null hypothesis. And oh yeah, don't forget, you got to check the conditions with each part of that. So once again, why is a sampling distribution so important? Because honestly, the most important factor in all of this is that we must assume the null hypothesis to be true and build a sampling distribution based on that value, right? Sampling distributions don't just show you one sample proportion, they show you all of them. And oftentimes with big populations, there are millions of p-hats out there. So this sample shows tons and tons and tons of p-hats. And that's why the sampling distribution is so important. Because once I make the sampling distribution, then I could look for my evidence. Is my sample way over here, showing that it's pretty significant? Or is it in the middle, showing that it's, likely? It's not a weird sample, assuming that the null is true. Again, the next topic will go into that a lot more detail. But right now, we just need to know how to build a sampling distribution. Here's a quick summary of how to build a sampling distribution. We did this back in Unit 5. Should be pretty easy. The first thing we need is the mean. The mean of all those p-hats should be the true p, the true proportion that we know from the null. But again, we do have to make sure the samples are random to avoid bias. The standard deviation of all those p-hats. Remember, some of those p-hats are going to be a little higher, some are going to be a little bit lower. The standard deviation is the giant square root, p times 1 minus p divided by n. Very simple formula. But again, this formula is only going to work if we have independence. So we need our sample size to be under 10% of the population so that we can assume independence. Lastly, we need the shape to be normal. We need a normal model for our sampling distribution. And that is going to be true as long as we have 10 or more successes and 10 or more failures in our sample. Now remember, success and failures are very generic terms. In a specific problem, you would define success and failure as what you're looking for and what you're not looking for. All right. Honestly, guys, these are the 2 steps I need you to walk away from this video understanding. Step 1 involves 3 things. They're all very easy. Identify the parameter of interest. You're just stating what the proportion you're interested in the problem is. Name the test, a one sample z test for a population parameter, and then write the null and the alternative hypotheses. Step 2 is checking the conditions and building the sampling distribution, assuming the null is true. Let's go back to the original problem I gave in the very beginning, and let's quickly run through the first 2 steps. Once again, medical journal says that 35% of adults experience depression sometime in their lives. David, the mayor of a large town in Vermont, thinks in his town it's lower. So he's going to select a random sample of 350 people, and he's going to try to prove it. All right, step 1 is to identify the parameter of interest, name the test, and write the hypotheses. Let's show you that. The parameter of interest is the proportion of adults that have experienced depression at some point in their lives. All you got to do is copy that from the problem. Then we have to name the test. This is a one sample z test for the proportion of adults that have been depressed. And then the null and the alternative are very easy. The null is that what we read is true. The alternative is the mayor's belief that his town is less than 35%. All hypotheses in every problem use P, and they all use the same number, in this case 0.35. You're never going to have different numbers between the null and the alternative. The only difference is the null always uses an equal sign, whereas the alternative could be less than, greater than, or not equal to, all depending on the problem. All right, step 2 is to find the mean, the standard deviation, and the shape of the sampling distribution. So the mean is the mean of all p hats, which, if 35% is true, that should put 35% right smack dab in the middle, the mean of all of them. The standard deviation of all the samples, because again, they're going to vary, is 0.35 times 0.65 divided by the sample size. It said the mayor was going to use a sample of 350. So you do need your calculator for this. I don't know, unless some of you out there are good enough to do this math in your head. I know that I'm not. But we do get 0.0255. So, for the sake of your picture, I don't ever encourage too much rounding, but for the sake of the picture, if you want to round that to about 3%, that'd be 0.38, 0.41, 0.44, down 0.32, down 0.29, down to 0.26. All right, and then of course the shape of the distribution is going to be normal. How do I know? Because of the 350 people, if 35% are supposed to be depressed, according to that article, that's about 123 people, more than 10 successes, people who are feeling depressed. And of those 350 people, 65 should be not depressed. And that number is also way bigger than 10. It's at about, I'm doing the calculation right now, sorry, about 228, okay, rounding those numbers a little bit. But they're both clearly bigger than 10. Don't forget that the samples do need to be random to avoid bias. Don't forget that the sample size needs to be under 10% of all the population of this town. It did say it was a large town, so I could assume independence. And again, the sampling distribution is going to be normal. All right, guys, the next step that you're going to learn about in the next video, I'll give you a little preview, is simply collecting your sample proportion. Now, I don't want to give it away because we'll talk about it in the next video, but once you have your p hat, what you're going to do is you're going to look for it. Is it in the middle? If it is, well, then you know what, guys? Sorry, the mayor's wrong. Because if your p hat falls in the middle, then it's not special. It's not significant. It's not unlikely, which means that 35% is probably true for this town. But if our sample is unbelievably high or unbelievably low, then we might have evidence that the mayor's correct. Now, obviously the mayor thinks it's lower, right? So I'm not going to look at this at all because that would actually completely prove the mayor wrong. So I'm looking, or at least the mayor's looking, for a sample way down here. Because if a sample falls significantly low, then the mayor might have that evidence that his town is really lower than 35%. But more on that in the next topic. All right, guys, that's it for this video. See you at topic 6.6. Or 6.5. Sorry, this is 6.4. All right, see you.